Welcome to Clinical Capsule, your trusted guide for clear and concise medical learning.
Okay, let's just jump right into this explainer. Think about the human heart as a high-performance engine. Normally, it just beats steadily, right? It easily adapts to whatever physical stress we put it under. But what actually happens when that engine gets fundamentally damaged? Today, we're unpacking a really fascinating but honestly pretty tragic chain reaction that goes down in the body. We're focusing heavily on the pathophysiology of heart failure, and specifically, the absolute double-edged sword of cardiac compensation.
So, to really grasp this biological irony, we have to start with a massive fundamental question. If the heart is so incredibly resilient, why does just a single injury often lead to a lifelong, progressive decline? Like, why doesn't it just heal up like a cut on your arm or a broken bone? Well, the answer is kind of wild. It lies in how the body's frantic attempt to fix a broken heart is literally the exact thing that ends up destroying it over time.
Our roadmap for tracking this tragic domino effect today is straightforward. We'll quickly define heart failure, look at the triggering index event, explore this idea of a compensatory illusion, dive into the cellular changes, and wrap up with the mechanisms of left ventricular remodeling.
All right, first up, defining exactly what heart failure is.
Now, looking at the ACCF and AHA guidelines, we see that heart failure isn't just one simple disease. It's actually a highly complex clinical syndrome. Basically, it results from any structural or functional impairment that messes with the ventricle's ability to either fill up with blood or eject it. So whether the heart muscle is just too weak to squeeze, or maybe it's too stiff to relax and fill properly, the end result is exactly the same. The heart simply cannot pump enough blood to meet the body's baseline demands.
Moving on to part 2, let's talk about the triggering index event.
You can think of this moment like our engine suddenly blowing a cylinder. The absolute starting point of this whole timeline is always what we call an index event. This is the definitive catalyst. It's an initial hit that damages the heart muscle directly, literally killing off functioning cardiac myocytes, or it disrupts the myocardium's ability to generate force. Either way, the heart can no longer contract normally.
And what actually causes this index event? Well, it comes in a few different flavors. It might strike abruptly, right, like a myocardial infarction, a heart attack, where blood flow is just cut off, causing instant tissue death. Or it could be a slow burn. It could build up gradually through chronic hemodynamic pressure or volume overload. Think long-standing high blood pressure or a leaky valve. It can even be hereditary, driven by genetic cardiomyopathies where mutations mess with the heart's structural proteins. But look, whether it's sudden, gradual, or genetic, every single one of these culprits shares one vital consequence. They cause a massive initial drop in the heart's pumping capacity.
Which brings us to part 3, the compensatory illusion.
And man, this is a real double-edged sword.
So, the heart takes a hit, pumping capacity drops, and we get a classic problem reaction sequence. The body immediately senses this dangerous drop in output and blood pressure, and it panics. It instantly activates these massive compensatory mechanisms, mainly the sympathetic nervous system and the RAAS, the renin-angiotensin-aldosterone system. These systems completely rev up whatever heart function is left. They spike the heart rate, clamp down on blood vessels to keep pressure up, and scream at the kidneys to hold on to salt and water to boost blood volume. And you know what? In the short term, it totally works. It brilliantly restores cardiovascular function right back to a normal homeostatic range.
But here's the profound irony. These compensatory systems work so incredibly well that the patient can walk around completely asymptomatic for months, sometimes even years. They feel absolutely fine, but it's a total illusion. These biological fixes are actually masking the damage. Because the body is constantly flooding the system with adrenaline and hormones to keep the pressure and volume artificially high, it is silently, relentlessly overworking an already damaged heart. It's forcing the engine to constantly run in the red line just to maintain a baseline.
Now for part 4, let's zoom in on the hidden toll, the cellular and myocardial changes. If we actually compare a healthy myocyte to a failing one, the microscopic changes are just catastrophic. That sustained neural hormonal activation we just talked about, it literally rewrites the cell's biology. We see a huge drop in the function of a protein called SERCA2a. Think of this as the cell's crucial calcium pump. With this pump failing, the cell takes in way less calcium, and at the exact same time, calcium starts leaking out of the sarcoplasmic reticulum. This completely ruins the cell's ability to contract and relax. And here is the truly mind-blowing part. In a desperate bid to survive this stress, the cells actually revert to fetal gene expression. They swap out their healthy adult proteins for older, weaker fetal ones. It's a crazy evolutionary fallback, but it just accelerates their own death. the cell's internal skeleton breaks down, leading to progressive necrosis and apoptosis. The literal building blocks of the heart are just falling apart under the strain.
Finally, part 5. We zoom back out to look at the mechanisms of left ventricular remodeling.
This is really the climax of the story. The gross structural pathology of a remodeled, failing heart is pretty shocking. The organ has been completely physically warped by that continuous mechanical burden and relentless neurohormonal stimulation. It is just no longer the compact, efficient pump it used to be.
The architectural consequences are incredibly stark. The left ventricle dilates. It literally balloons outward. It morphs from this tight, muscular football shape into a thin-walled, bloated basketball. This increased sphericity and wall thinning cranks up the afterload, creating this awful mechanical mismatch that further tanks the stroke volume. And it gets worse. As the ventricle stretches out, it physically pulls the papillary muscles apart, leading to functional mitral regurgitation. So now the valves aren't even closing properly. Blood is flowing backward, creating an even more massive mechanical burden that the heart simply cannot overcome.
So, tracking this whole thing chronologically, you can really see the tragic domino effect at play. At time 0, bam, the index event, the initial cardiac injury. Then, we enter this phase lasting months or years, the asymptomatic phase. This is where those short-term fixes create a dangerous illusion of health. But beneath the surface, there's relentless, progressive left ventricular remodeling causing severe end-organ damage. Ultimately, this crashes into the end stage, cardiac decompensation. This is when the heart just can't keep up the act anymore, and those overt, debilitating symptoms finally show up.
It absolutely boils down to this harsh reality. Sustained activation of these systems leads to secondary end-organ damage within the ventricle, with worsening left ventricular remodeling and subsequent cardiac decompensation. The tragic irony is complete, right? The very biological systems meant to save the heart are exactly the things that destroy it.
So, as we wrap up this explainer, I want to leave you with a pretty provocative thought. If left ventricular remodeling is the ultimate culprit in this whole progressive decline, is it possible for us to halt, or maybe even reverse, this architectural damage? Like, if we can intervene early enough with therapies that block those overactive compensatory mechanisms, can we actually give the engine a real chance to heal itself? It's the massive question driving modern cardiovascular medicine right now. Thank you so much for joining me, and keep exploring the science around you.